Hello and welcome to lecture number 26 in the course Computer Graphics. We will continue our discussion on the graphics pipeline. For a quick recap, let us just go through the stages. So, we have already discussed the first stage, that is object representation, second stage modeling transformation, third stage lighting, fourth stage viewing pipeline, and the only stage that is remaining is the fifth stage, scan conversion. We are currently discussing the fifth stage. In the last lecture, we talked about rendering of lines, which is part of the fifth stage, and there we talked about a very intuitive approach as well as a slightly improved approach, that is the DDA methods. Today, we will continue our discussion on line rendering, where we will talk about even better approach, and also we will discuss rendering of circles. Now, before we go into the discussion on a better line rendering approach, let us quickly recap what we have seen in the previous lecture on line rendering. So, the idea was to map a description from viewport to a pixel grid. That is of course, the objective of the fifth stage. In order to do that, simplest approach is just to round off the real coordinates to the nearest integers, which are pixels. For example, from 2.3, 2.6 to 2.3. Now, this is good for points, but for mapping lines or circles or other primitive shapes, this may not be good. And for line, what we did? So, we first assume that a line segment is defined by the endpoints, and our objective is to map all the points that are on the line to the appropriate pixels. The straightforward approach that we discussed is that first we map the endpoints to pixels, then we start with one endpoint which is having the lower x and y coordinate values, then we work out y coordinate values for successive x coordinates, where the x coordinates differ by 1, because we are talking of pixel grids, and then these y values that we computed are mapped to the nearest integers, thereby getting the pixels. Now, this approach has two problems. First, we require multiplication, which is a floating point operation, and secondly we require rounding off, which is also a floating point operation. Now, these floating point operations are computationally expensive and may result in slower rendering of lines. To improve, we discussed one incremental approach. There we did not go for multiplication, instead we used addition. So, to compute y, we simply added this m value to the current value, or to compute x, new x, we simply added this 1 by m value to the current x value. Now, when to choose whether to compute x or y, that depends on the slope. So, if the m value is within this range, then we compute y given x, otherwise we compute x given y using the line equation. Now, the DDA can reduce some floating point operations, as we have discussed, particularly multiplications. However, it still requires other floating point operations, namely additions and rounding off. So, it is still not completely efficient, so to speak, and we require a better approach. One such approach is given by Bresnham's algorithm. Now, this is an efficient way to scan convert line segments, and we will discuss the algorithm assuming M to be within these ranges. That means, we will concentrate on computing y value given the x value. Now, let us try to understand the situation. Suppose this is the actual point on the line and we are moving along the x direction. The current position is given by this point x k y k. Now, the actual point on the line is a floating point number, real number. So, we need to map it to the nearest pixel grid point. Now, there are two potential candidates for that. One is this pixel or the upper candidate pixel, that is x k plus 1, y k plus 1, and the other one is the lower candidate pixel, that is x k plus 1 y k, and we have to choose one of those. How to choose that? Our objective is to choose a pixel that is closer with respect to the other pixel to the original line. So, between these two pixels we have to decide which one is closer to the original line and choose that pixel. Let us denote by d upper the distance of the pixel x k plus 1 y k plus 1 from the line, that is the upper candidate pixel from the line as shown here. Similarly, d lower indicates the distance of the lower candidate pixel from the line. Now, at x k plus 1, that is at these points, y is given by this expression using the line equation, where m is the slope. Then we can say that d upper can be given by y k plus 1 minus y, that is this value minus this y value, which is given here, or this expression. Similarly, d lower can also be given as y minus y k, as you can see here. This is the y value and this is the y k value. So, replacing the y from this equation, we can get this expression. Now, let us do some mathematical trick on these expressions. But before that, we should note that if the difference is less than 0, then the lower pixel is closer and we choose it, otherwise we choose the upper pixel. Distance between the y values here, here and here, the two distances that we have used in expressing d upper and d lower. If the difference is less than 0, then we choose the lower pixel, because that point is closer to the line, otherwise we choose the upper pixel. Now, let us substitute m with this ratio delta y by delta x, where delta y is the y coordinate difference between the endpoints and delta x is the x coordinate difference between the endpoints. And then we rearrange and replace this expression with c, which is a constant term. As you can see here, all are constants. Then what we get? This term to be equal to this term. Both sides we have multiplied by delta x and replace m with these expressions. Rearranging and expanding, we get this, then we replace this constant term here with c to get this expression. This is a simple manipulation of the terms. Now, let us denote the left hand side by pk. We call it a decision parameter for the kth step. Now, this parameter is used to decide the closeness of a pixel to the line. Now, its sign will be same as that of the sign of the difference d lower minus d upper. Thus, if pk is less than 0, then this lower pixel is closer to the line and we choose it, otherwise we choose the upper pixel. So, that is at step k. Now, at step k plus 1, that is the next step, we get pk plus 1. Now, that is essentially given by this expression, where we replaced xk with xk plus 1 and yk with yk plus 1. These two terms we replaced with the next term. Then we take a difference between the two, pk plus 1 minus pk, which gives us this expression. Now, we know, because we are dealing with a pixel grid, that xk plus 1 is essentially xk plus 1. So, we can rearrange and rewrite the expression as pk plus 1 equal to pk plus twice delta y minus this term. That means, the decision variable at k plus 1th step is given by the decision variable at kth step plus a term, this entire term. Now, if pk less than 0, that is the lower pixel is closer, then we set yk plus 1 equal to yk, otherwise we set yk plus 1 equal to yk plus 1. Thus, based on the sign of pk, this term becomes either 0 or 1. So, you can see the physical significance from this figure. So, if pk is less than 0, that means in the current stage lower pixel is closer, that means we have chosen this one. Then in the next stage we have to choose yk plus 1 equal to yk, that is the lower pixel. If that is not the case, then we have to choose yk plus 1 equal to yk plus 1, that is the upper pixel. So, depending on the sign of pk, this term yk plus 1 minus yk turns out to be either 0 or 1. If pk less than 0, then this is 0. If pk not less than 0, then it is 1. So, where we start? Then we have to decide on the first decision parameter, and that we call P 0, which is given by twice delta y minus delta x. This value we calculate and then we continue. So, the overall algorithm is given here. We first compute these differences between the endpoints and the first decision parameter. Then we go inside a loop till we reach the endpoint. We start with one endpoint and till we reach the other endpoint, we continue in the loop. Now, if p less than 0, we set that difference to be 0 and then update p as p plus twice delta y. If p is greater than equal to 0, then we update p as given in this expression. And then add the corresponding x y value into the set of pixels, that is the output of the algorithm. So, depending on the decision value, we choose a pixel and add it to the set of pixels. Now, here we assume that m is within this range. When m is outside this range, we have to modify this algorithm, but that is a minor modification. So, you may try it yourself. So, what is the advantage of this algorithm? Here, if you note, we are choosing the pixels at each step depending on the sign of decision parameter, and the decision parameter is computed entirely with integer operations. So, there is no floating point operation. Thus, we have eliminated all floating point operations, additions, rounding off as well as multiplications, which is a huge improvement, because in reality we need to render large number of lines in a short span of time, very short span of time. So, there this saving is substantial. There are even better approaches, but we will not discuss those any further. Now, let us try to understand the algorithm in terms of one example. We will continue with our example that we have introduced in the previous lecture. So, this is the line segment given, these are the endpoints already mapped, and our job is to find out the intermediate pixels that correspond to the points on the line. So, we will start with computing delta x, delta y and initial p. Then we start with one endpoint and add it to the list of pixels, the endpoint. Now, we have computed p to be 1, which is greater than equal to 0. So, here the upper pixel is closer, that means we choose this one. We add this and update p with the expression to be minus 3, and 3 is added to the grid. Now, this is not the end point, we have not yet reached the end point. So, we continue. In the second execution, we check that p is minus 3, which is less than 0. So, in the second case, the lower pixel is chosen and we update p again to be 3, add this lower pixel to the output list and check whether we have reached the endpoint. Since we have not yet reached, we continue the loop, and in this way we continue to get other points. So, in the next stage p equal to 3 greater than 0. So, we choose the upper pixel, add this one to the output pixel list, continue the loop since we are yet to reach the end point. Then we find p to be -1 less than 0. So, we choose the lower pixel, add the pixel to the output list, and now we see that we have reached the other end point. So, we stop the loop and add the other end point into the list. That is our last step. So, finally, what are the points that we get? These are the pixels that we get following the steps of the Bresnham's algorithm. Now, you can compare it with the previous methods that we used. However, while comparing, you should keep in mind the number of floating point operations that we avoided, because that is the advantage. So, if you find that both the sets or all the sets that we have found earlier are same, that is not a problem, because we saved in terms of computation. So, with that we end our discussion on line scan conversion. So, we learned 3 things. First, we started with a simple approach, found its problems. Then we discussed one improved approach, that is the DDA approach, and then we finally discussed even better approach, the Bresnham's line drawing algorithm, which eliminates all the floating point operations. Now, we will move to scan conversion of another primitive shape, that is circle. Initially, we will assume that the circle is centered at origin with a radius r, and its equation is given by x square plus y square equal to r square. We all know this equation. Now, in the simple approach, the most intuitive and straightforward approach, what we do? We solve for y after every unit increment of x in the pixel grid by using the equation. Clearly, here we have lots of computations, floating point computations, which involve square root and multiplications, because r need not be integer. So, this is inefficient. We may also need to round off the computed values, which is addition of other floating point operations, and the pixels that we obtain may not generate smooth circle, because there may be gap between actual points and the chosen pixels after rounding off. So, it suffers from many problems, and we require a better solution. Let us try to go through one such solution, which is called the midpoint algorithm. Now, this algorithm exploits an interesting property of circle, that is called 8-way symmetry. Now, what is this property? If we look at this figure, we will see that this is the origin and the circle is around the origin, we can divide the circle into 8 quadrants. These are the quadrants, and if we determine one point on any quadrant, say this point, then we can determine 7 other points on the circle belonging to the 7 quadrants without much computation. So, if this point is x y, then we can say this point will be y x, will be y minus x, this one will be x minus y, this one will be minus x minus y, this one will be minus y minus x, this one will be minus y x, and this one will be minus x y. This we can straight away determine without any further computation. We can exploit this property in circle scan conversion by computing one point on a quadrant and then use that point to derive the other 7 points on the circle. That means, we determine one pixel and from there we determine the other 7 pixels. So, instead of determining the pixels through computation 8 times, we do it once and the other 7 time computations we save. Now, let us see how to determine a pixel for a given quadrant. Suppose we have determined a pixel xk yk. Now, this is one quadrant of the circle given. Now, next pixel should be either this one or this one. Again we can call them upper candidate pixel and lower candidate pixel. And in this case, note that we are going down along this direction, down the scan lines, and our objective is to choose a pixel that is closer to the circle. Now, how do we decide which of these two candidate pixels is closer to the circle? Again we go for some mathematical trick. Now, the circle equation we can reorganize in this way: f x y equal to x square plus y square minus r square. This is the circle equation, we can restate in this way. Now, this function we can evaluate as shown here, that is f x y is less than 0 if the point x y is inside the circle, it is 0 if it is on the circle, and it will be greater than 0 if the point is outside the circle. This we know from geometry. Then we can evaluate the function at the midpoint of the two candidate pixels. That means, at xk plus 1 and yk minus half. Note that this is yk, so midpoint will be this point, that is yk minus half, and it will be xk plus 1, that will be the new x coordinate. Now, this will be our decision variable pk after k steps. So, let us try to see what this variable looks like. So, essentially we compute this function at the point xk plus 1 yk minus half, which is the midpoint between the two candidate pixels, and y half because this is the unit distance. So, half or the midpoint will be half of this unit distance. So, pk will be the function value at this point, Now, if we expand the function with these coordinates, then we get this expression, which is the expression for pk. Now, if pk is less than 0, that means the function evaluates to be less than 0, then we know from the geometric property that midpoint is inside the circle. That means the upper candidate pixel will be closer to the circle boundary. So, we choose xk plus 1 yk. If that is not the case, then we choose the other candidate pixel, that is xk plus 1 yk minus 1. Note that we are going down the scan lines. So, next y coordinate will be yk minus 1, because in that case midpoint is outside and this lower candidate pixel is closer to the boundary. Now, let us see the expression for the decision variable at the next step, that is pk plus 1. So, here our new point will be xk plus 1 plus 1 increment by 1 and yk plus 1 minus half, which after expansion will look like this. Now, we may expand it further and then rearrange to get a simplified expression, that is pk plus 1 is the current decision value plus this term. Now, yk plus 1 is yk if pk is less than 0, that we have already seen. So, in that case pk plus 1 will be pk plus 2 xk plus 3. Now, if pk greater than 0, then yk plus 1 will be yk minus 1, that also we have seen. Then the pk plus 1 term will become something like this. As you can see, these are all integer operations. And we choose the pixels based on an incremental approach, that is computing the next decision parameter from the current value, and that too by avoiding floating point operations. However, that need not be the case, because here the initial decision parameter or decision variable involves floating point operation, and we have to keep that in mind, that unlike the Bresnham's algorithm, although the expression for computing the next decision variable does not involve any floating point operation apparently, but when we start with maybe a floating point value, and then that will remain. So, here we are not completely eliminating floating point operations, but we are reducing them significantly. So, what is the complete algorithm? We first compute the first decision variable, and choose the first or the starting point. Now, one point we have chosen, then using symmetry we can add 4 other points or pixels. Now, when the decision parameter is less than 0, we update the parameter in this way and get the pixel to add to the set of pixels. When the decision parameter is greater than 0, then we update the decision parameter in this way and get this point as the new pixel. And then we add the new pixel to the list of pixels, plus we add the 7 symmetric points. using the symmetric property, and we continue it until we reach the end of the quadrant. So, that is how midpoint algorithm works. As you have noted, if we go for simple approach, we require a lot of floating point operations, multiplication, square root, which we avoided by this midpoint algorithm. Now, here of course, it may be noted that the algorithm assumes circle is centered at origin, and we require some modification when we are assuming circles which has its center at any arbitrary location. But that minor modification we will not go into the details, you may try it yourself. Now, let us try to understand this algorithm better in terms of one illustrative example. Let us start with the assumption that we have a circle with radius r to be 2.7, that means a real number. Now, let us execute the algorithm to find out the pixels that we should choose to represent the circle. First stage is compute p, which is 5 by 4 minus r, which gives us this value, and we start with this point by rounding off r to 3, and we get this point as the first point in our list, first pixel, and based on this first pixel we add other 4 pixels in the output list. Then we enter the main loop. So, we have p less than 0, then we update p as per the expression for p less than 0, and then get this new pixel value. With that we add 8 pixels to the output list, 1 3, 3 1, 3 minus 1, 1 minus 3, and so on. Since we have not yet reached the end of the loop, we continue with the loop. In the second loop run, we have p greater than 0. So, we use the expression to update p, and we get the new value, and we decide on this new pixel. Based on that, we choose the 8 pixels as shown here. Now, we have arrived at the end of the loop, the termination condition is reached. So, we stop. So, then at the end what we get? We get 20 pixels shown here. One thing you may note is that there are some pixels that are repeated. For example, 2 2 occurred twice, minus 2 2 occurred twice, 2 minus 2 occurred twice. So, this repetition is there at the end of the execution of the algorithm. These duplicate entries we need to remove. So, before rendering we perform further checks and processing on the output list to remove such duplicate entries. So, the algorithm may give us a list having duplicate entries. We need to perform some checks before we use those pixels to render the circle to avoid duplications. So, that is what we do to render circle. So, we have learned how to render line, we have learned how to render circle. In both the cases, our objective was to map from real number values to pixel grids and our objective was to do so without involving floating point operations to the extent possible, because in practical applications we need to render these shapes very frequently, and there if too many floating point operations are involved, then the speed at which we can render may slow down, giving us the perception of a distorted image or flickers which are unwelcome. In the next class, we will discuss more on rendering other things. Whatever we have discussed today can be found in this book.